So, good morning. We shall start the first hour lecture on the formal languages, automata, and codes. And this part of our course will be preliminary lectures. We give an account of some basic notion which will be used throughout of our course. So, usually by and that Q, R, and C with another set of negative non-negative integers, rational, real, and complex numbers, respectively. By convention, we assume that 0 is an element of n. Also, we put that R with plus. It consists of such real numbers x, so that x are equal or greater 0. Also, by the symbol NP, by binomial coefficient of n and p, we mean the following fraction: n factorial divides to p factorial n minus p factorial. Also, for real numbers x equal or less y, we denote by such symbol here, or such array, the set of real numbers s, so that x is equal or less z. Hello everyone, we shall start our lecture. Що тут таке робиться з тою? Та-та-та-та. Що за звук? We shall start. Hello everyone. Today we start our new course of formal languages, automata, and codes. And our first lecture will be devoted to introductions. This course some new definitions. So we shall start. This part of preliminary lectures, we give an account of some basic notion which will be used throughout of our course for formal languages, automata, and codes. As usual, by N, Z, Q, R, and C capital, we denote the set of non-negative integers, rational numbers, real numbers, and complex numbers, respectively. Also, we suppose that 0 is an element of n capital. Also, we denote by R sub plus is such real numbers x that are equal or greater than 0. And by symbol, we shall denote the binomial coefficient of n and p, which is equal the n factorial divided by p factorial n minus p factorial. For real numbers x and y, such that x is equal or less y, we denote by array x, y, which start with x, the set of real number z, such that x is equal or less z and z is less y. When we have that x is equal y, then we assume that this set array from x to y is empty set. For any two subset x and y of the set z, we denote set minus y or x without y is consist of such element of the set z, such that z is element of x, but z is not element of y. Frequently, x with our line, which we use it to denote the complement of a subset x of some set z. Element small x and the singleton set sub x will be usually not be distinguished. So also we use it for the denomination of a singleton set which consists from z and the element x. Also the set of all subset of this set x we denote by p Gothic P from x by the following symbol. The function symbol are used writing on the left of the argument, but with some exception. So we should, if we have some function here, for example, y is equal f of x, we shall write the symbol of some function f from the left, yeah. But when we consider the composition of x on the set, the action is written on the right. So in our case, we shall write if we have two actions of the set alpha and beta from the set x to x, we shall write the image of element x from x by alpha x here, and we shall write the symbol by beta. Also the composition in our case of the such two action, we shall write alpha composition beta, and the image we shall write in the following, or also we shall write the action of alpha, then alpha action of beta, in particular permutation are written on the right. So what is permutation? This is thought bijective map. What is a permutation? If we have x is an empty set here, we can consider a map which satisfies the following property: f from x to x, and this map has the following two property. First property, that f is injective. What does it mean? That if we have x and y from x here, and x is not equal y, then we have this implies that f of x is not equal f of y. So also the second property is bijection or bijection. So f is bijective if for any y from x there exists x from x such that the image of x by f is equal to y. In this case, when map from x to x satisfy these two property, equal as that f is injective and f is bijective, then map x is called bijection or bijective. When the set x is finite, we shall call such maps permutation of x. So a partition of this set x is a family x sub y of a non-empty subset of x, such that the following condition holds: x is equal to the union of xi, and for distinct y and j, the intersection of xy and xj is an empty set. So we usually define a partition in the following way: let x is the union of x I belongs to I capital, be a partition of x. Also, we denote the cardinality of the set x by card x. What is the cardinality? When we have that x is finite set, what is finite set? If the element of x we shall denote by a1, a2, a3, and so an, where n is some non-negative integer. Maybe here, right, we shall start a0 and so on, yeah? Then we shall write that the cardinality of x is equal n plus 1. Well, is the usual calculation of elements of the set x. Also, we shall write the cardinality of two sets A and B coincides. The cardinality of A is equal to the cardinality of B if there exists a bijection from A onto B. And in this case, we shall say that A and B have same cardinality. Also, we shall tell us the following, that if the cardinality of set A coincide with the cardinality of the set of all non-negative integers, then we call this A is infinite, and also A is countable. If the A is equal to the cardinality of the usual interval from 0 to 1 of real numbers, then we write that the cardinality of A is continuum. We shall write this as small c small Galactic C. In this case, we shall write that the cardinality of A, or the set of non-negative integer, is equal aleph null, aleph 0, or omega 0, or is same omega 0. So when x is finite, the cardinality is the numbers in the number of its elements. Yeah. Good. What is semigroup? A semigroup is a set equipped with the associated binary operation. What is binary operation? So if we have S is a set, we can see the map from S square, Cartesian square, the Cartesian product from S by S to S. We shall this map denoted by mu, and any map from S from this Cartesian product to S is called a binary operation on S. Also, if simply this operation we shall denote the following way: for any A and B from S, we will write that mu AB is equal AB, and this operation C dot we shall call multiplication. If this operation is associative, what does it mean associative? So associativity is the following property. If we first find mu of A and B, then we calculate mu of this result and C. This is equal mu A mu BC. Also, algebraists write this formula in the following: A multiply B multiply C is equal A multiply B multiply C. This means that first we calculate A multiply B, then this result multiply by C, and in this case we should first we calculate B multiply C, and after that we calculate A multiply this result. So in this case, operation is called associative. So, and when we have a binary associative operation on set S, then the set S with such operation is called a semigroup. Yeah. So first, very simple examples. If we consider the set of non-negative integer with usual addition, is a semigroup. Also, if we consider R, a set of real numbers with usual, this is a semigroup. If we consider R or any numbers with operation multiplication, usual multiplication of real numbers, is a semigroup. So we shall write as an associative binary operation is all following when for any A, B, C from set on the set from the set S. Yeah. And everyone we shall write usually this operation in multiplicative case, so in such a way. Yeah. And we shall, everyone, we shall tell that in this case that this product is also this operation we shall call the product. Also, we shall call that this operation is a multiplication. What is a monoid? A monoid is a semigroup which, in addition, has a natural element or a unit element. What is a unit element? An element A of the semigroup S is called unit or natural element if the following condition holds, that A multiply B is equal B multiply A is equal B for all B from S. In this case, we shall call A a natural or the unit element of the semigroup S. The natural element of a monoid is unique, and later we shall denote it by 1 sub m or simply 1. Why is unique? The proof is very simple, and I propose this proof for you. So suppose there exists a semigroup S, a monoid S which contains two unit elements, 1, 1 and 1, 2, yeah? Since element 1, 1 is a unit element, we have that 1, 1 multiply 1, 2 is equal 1, 2, yeah? Because element of the monoid as 1, 1 is unit element. Here we have the following equation, yeah? But the element 1, 2 of the monoid M is the natural element, and hence we get this equal 1, 1. This implies that 1, 1 is equal 1, 2. And hence, in any monoid M, there is only one natural element. For any monoid M, the set P-Gothic of N is given a monoid structure by defining for any subset X and Y from N the following operation: X multiply Y, X capital multiply Y capital. We here left the operation of multiplication. This consists from X multiply Y, so that X from X capital and Y from Y capital. So in the case of monoid P-Gothic M, the natural element is singleton set. It consists from the natural element of the monoid M, yeah? A submonoid of a monoid is a subset and which is stable under the operation, under the monoid associative binary operation, and which contains the natural element M of the monoid M, yeah? That is 1M belongs to N, and more or N multiply N is a subset of N. This means the following, that the set N is algebraic closed in M. What does it mean? This means the following. If we have two elements A, B from N, yeah, for any A, B from N, A multiply B belong N, where N is our subset, usual subset, yeah, of the monoid M. Also, we give next week give some example a submonoid of monoid, and before that we consider the following semigroup. We consider the set of non-negative integers and with the operation maximum. What is the operation? It's a very simple operation. X for any xy from n, we have x multiply y is equal maximum of x and y. The first exercise for you will be to show that operation is associative. It's very, very trivial exercise, and I propose to solve you it. If we consider in this set the following subset, we shall denote M5. What is this? It's N capital without 0, so on 4, yeah, 1, 2, 3, 4. Then, of course, the maximum of two elements of M5, the product of any element of M5 is an element of M5, yeah? But the natural element of N5 is 5. Because if you consider any element of M5, 5 multiply x is equal x, or x multiply 5 is equal x, because 5 is equal or less of any element of M5. But what we have is the unit element of M5 is not unit element or of n maximum, yeah? So because 1 multiply 5 is equal 5, and this contradicts the definition of unit element. So in this case, we shall call that M5 is a subsemigroup of n max or n maximum, but M5 is not a submonoid of n maximum. What is morphism from monoid into M from into monoid n? Is a function or a map, yes, phi from n to n, which satisfies the following two properties. For all m prime from m, we have that phi of m multiply m prime is equal phi of m multiply phi of m prime, and the image under phi the natural element of monoid m is in the natural element of monoid n. So if we have monoid and submonoid, similarly we can introduce the notion subsemigroup. So what is a subsemigroup? Is a semigroup. So if we have S is semigroup, yeah, then any subset n of S is called a semigroup if the following condition holds. Yeah. So this first condition when a subset is a submonoid of a monoid, yeah. And similarly, we have a map from a semigroup M to semigroup N, which satisfy this condition. This map is called a semigroup morphism. Also, we remark that a morphism in algebraic semigroup theory, many specialists in this topic is called a homomorphism. So if I write or tell you a homomorphism, such notion you study in the course of discrete languages, the discrete mathematics, or in the course of the computational algebra and geometry in the first year. And also we use this term. The homomorphism is morphism, yeah, the same for monoids or for a semigroup. What is congruence? A congruence on a monoid M is equivalence relation theta on M such that for all M prime from M capital and all U and V from M, that if M and prime are equivalent up to modulo theta, implies that UMV is equivalent to UM prime V up to modulo theta. So what is equivalent relation? This relation is a relation alpha on is a subset of the product X times X, and is called the equivalent relation if alpha is reflexive. This means the following. So XX belongs to alpha for all X from X capital. It's symmetric. What does this mean? If X, Y belongs to alpha, this implies that Y X belongs alpha to symmetric. And the set conditions is transitive. What does this mean? It means the following property. If X and Y Z belong to alpha, this implies that X Z belongs alpha. So we shall repeat that alpha is a relation of the set X is called equivalence, an equivalence or equivalence relation if it is reflexive, symmetric, and transitive. Also, this property is that when alpha is equivalence relation, we shall write or theta is equivalence relation on the set M. We shall write M is equivalent M prime up to modulo theta, yeah, on this way. Suppose phi is a morphism from monoid M to onto monoid N. And the equivalence relation theta defined by M equivalent M prime up to modulo theta if and only if the image of M and the image of M prime under the homomorphism phi is a congruence. So what does it mean? This equivalence means that the two elements are equivalent Yes, if and only if the image of these elements are same. Yeah. In this case, we shall call this congruence the nuclear congruence induced by morphism phi. Conversely, if theta is a congruence of the monoid M, then the set, the quotient set M by theta of the equivalence classes of theta is equipped with the monoid structure, and the canonical function from M to the quotient set is a monoid morphism. So what is idempotent of semigroup or idempotent of monoid? An element E of monoid M is called idempotent if E is equal E squared, or equivalent that E is equal E multiply E. For each idempotent E of a monoid M, the set EME, which consists of such elements of the form ESE, where S belongs to M, is monoid contained in the monoid M. It easily sees that the largest monoid, this monoid is the largest monoid which contains M and having E as a natural element. So we shall show that this set is a monoid. What does it mean? So if I consider any element x bar from EM, yeah, this element has the following form: EX multiply E, where X belongs to M, yeah. And similar, we have that Y from this set has the form EY, E from some Y from M. Then X bar multiply Y bar is equal X E EXE, yeah, multiply EYE, yeah. And the associated of binary operation implies that this product is equal EXE, yeah, YE. E in square is equal E. Or this, since this element with this underlying is element of the monoid M, and hence we get that this element belongs to EME. So in this case, when M is a monoid and E is an idempotent of M, the subset EME with induced operation from M is called the monoid localized at the idempotent E. An element of a monoid M is called zero if it is different from the natural element, and for any element from monoid M, we have that the following condition holds: that 0 multiply M is equal M multiply 0 is equal 0. And I propose use the following exercise. Exercise 2, yeah, to show that every semigroup homomorphic has at most one zero. 1, 0. Okay. The proof of this statement is very simple, and it's similar to the proof that every monoid contains at most one natural element. What does this sense? Yeah, I propose to prove. Next, let M be a monoid. The set of left or right invertible element of X is called the group of units of M. What is invertible elements of a monoid? Maybe we should start the following property. So if we have monoid M, yeah, with unit element 1, we shall call that X is invertible to Y. Give the following condition for X, Y is equal Y, X is equal the natural element 1, yeah? And in this case, we should say that Y is right invertible to X, in this case, yeah? If this condition holds with equality, and if this inequality, we shall say that Y is left invertible to X. And if M is monoid, it contains at least one invertible element that is the natural element. What is the cyclic monoid? So if we have that a monoid M with the following property, that all elements of monoid M has so property, then we shall write that all element has a form A in the power n, where n is from as a set of non-negative integer, at least that A in power 0 is equal to 1, equal as that the natural element of M. In this case, we shall say that M is a cyclic monoid. Well, for example, very simple example. So if we consider the element or the set of non-negative integers with the usual operation addition, then 0 as an integer of n is natural element, is a natural element. Element of n plus, yeah. But if we consider usual identity as numbers, as real numbers, yeah, is this number generate this monoid n plus. So what we have? So we, in our case, we consider the monoid such that n with such operation addition, yeah, it has the following properties that all power of number 1 is distinct, yeah. And hence we get that this monoid is infinite. We have very nice properties that if we have a cyclic monoid M, it is infinite, then it is isomorphic to the additive monoid N of non-negative integers. Okay, what we what is an isomorphism? So an isomorphism F from monoid S to monoid T is a map, is such map that F is morphism is a morphism, okay? And F is bijection. So, in other words, an isomorphism is bijective homomorphism. So, next we give an example of isomorphism. We can see the following. We can see we fix any positive real numbers. For example, it is so square of 2, yeah. And if we consider the set A in power n, where n is from the set of all non-negative integers, then there exists a very simple map which poset n to is equal A in power n. This map is from n with operation addition and to the monoid M. This map is an isomorphism. I propose you to prove this exercise. Exercise 3, to prove that such map from non-negative integer with operation addition to the monoid with usual multiplication real numbers, yeah, such monoid, yeah, where I is square of 2, yeah, we get root square of 2. This map is isomorphism. Good. Next. What we have when M is finite monoid. If M is a finite monoid, then the index of M is the smallest integer I, such that there exists some small non-negative integer I, yes, there exists an integer, positive integer R, and with the following property: I in power I plus R is equal AR. The smaller integer R in this case is called the pirate of the monoid M. The power composite of indexes I and pirate P determines the monoid having I plus P elements. These elements are written here, yeah, where 1 is the natural element of this monoid M sub IP. And the multiplication this monoid is conventionally represented in the following pictures. So we have A in power 1, A2, so on, A in power I, yeah, A in power I plus 1, so on, A in power I plus R minus 1, and A in power I plus R coincide with a in power I, yeah, where also 1 we denote the natural element of this monoid. We claim that monoid MIP contains two idempotent. In the case when I equal or greater 1. And it assumes that a in power j is equal a in power 2j, then j is equal 0 or j is equal or greatest I, and j and 2j have same residual mod by modulo p. Hence we have that j is equivalent 0 up to modulo p. Conversely, if j is equal or great I and j equivalent to 0 by modulo p, then we have that I in power j is equal I in power 2j. Conversely, the unique idempotent E distinct from the natural element of the monoid MIP is E a in power j, where j is a unique integer indices set from I to I plus p minus 1 is a multiply of p. Next definition, we need the following classical notion. If M is monoid, then for any element x and y we define two sets, x is the power minus y minus 1 multiply y, or we shall tell this call this terms in the form x minus 1 y is consist of such elements z from M, so that x multiply z is equal y, yeah. So this means that this set x minus minus 1 y consists of all solution of this equation xz x equal y, yeah. And similarly we get the following set x y minus 1. It consists from solution of the equation x is equal zy, yeah? If we have subset x and y of the monoid M, this notation we can extend to the following notation for the subset x and y. X minus 1, x capital minus 1, y capital consists of union of such element from y from y capital and x from x capital is similar to this. This notation x capital minus 1 y should be not confused from the product of the inverse of the element and another is the same subgroups. Also, for given subset of a monoid M, we define f of x m minus 1 x m minus 1, and this set f of x we shall call the set of factors of element in x. And of course f of x consists such element of the monoid M that there exists u and v from M such that u m v belongs to x. So a relation over set Q is subset of Q times Q. The product of Q relation M and N. Our Q is a relation M multiply N, and it's defined in the following way. As the element PR belongs to this product if and only if there exists small q from Q capital, that PQ belongs to M and QR belongs to M. And the set of all the relation of the set Q we shall denote it's by P capital Gothic Q times Q, yeah, is a monoid for this product, yeah. To remark on relation, identity relation, and then the null relation. So what is the identity relation in this case? Identity relation, which consists of power x from q, yeah. This is the natural element of such semigroup, and the null relation, yeah. What is the empty subset of the product q on q, yeah, q and q. This is a view that the empty set is a zero element of such semigroup, yeah. So we finish our lecture, and I wish you good luck.